Hello, everyone. Good morning, good afternoon, and good evening, wherever you are. I'm Shah Faisal, and this is the track 6 of Powering the Future Summit 2021, which is organized by IEEE Power and Energy Society Young Professionals. Today, our respected guest is Professor Felipe Lopez. He is professor in the Department of Electrical Engineering at Federal University of Paraíba. He is an IEEE senior member of the SIGRI Study Committee, B5 Protection and Automation. He is expert in the field of electrical power systems, mainly focusing on protection of electrical power systems, fault location on distribution and transmission systems, and electromagnetic transients and electrical power systems. Today he will talk about enhancing traveling wave-based application, being adaptive to be smarter. Please welcome Professor Felipe for further discussion on the topic.
Hello, everyone. Good morning, good afternoon, and good evening for everyone. It's a great pleasure, Shah, for being here today. I would like to thank for the invitation and to congratulate all of you for the organization of such a so nice event in the context of the young professionals in IEEE. So congratulations and thanks very much. So we can start. Okay. I will start my time here. I'm sorry, just a minute. Okay. So this is the title of my presentation, Enhancing Travel and Wave-Based Applications Being Adaptive to be Smarter. I am professor at the Federal University of Paraíba in the Alternative and Renewable Energy Center. And to whom that may not know me, I am from Brazil. I am 35 years old. Currently, I am an IEEE senior member. And as Shah have already said to you, I am a member of SIGRI Group B5, which is focused on protection systems. And since 2020, I had I have had the pleasure to coordinate the Brazilian SIGRI Mirror Group B555, which has worked on travel wave-based applications. And first of all, I would like to thank very much Study, Luis, Shah, for the invitation, and also invite all of you to follow us in our social networks like YouTube, Instagram, LinkedIn, Telegram, or even you can scan this QR code. We are always posting some news on our research and works. Okay. Let's start what really matters today. What we will talk about today, I will repeat here the title of this presentation: Enhancing Travel Wave-Based Applications Being Adaptive to be Smarter. But at this moment, I have to be sure that we are in the same page, and you must understand that we are talking about technological evolution. And if you know, when I was writing this title, I chose the two words that I consider that are very strong in this context, which are adaptive and smarter. Smarter is referring to like the word smart. So now I want to invite you to play a puzzle game, but you will not play alone. I will help you to play this game. We have three pieces here which we need to put in their right places. And we have a piece of evolution, we have a piece of adaptive, we have a piece of smart. We don't know where this piece must be placed in this game, but it's like a game of cause and consequence. We need to know what leads us to be what. And but as I mentioned, you will not play alone this game. I will help you to understand, and to do so, I want to start here my lecture talking a little bit about the Charles Darwin theory of evolution. Some of you may think that it's somewhat strange to talk about Charles Darwin theory of evolution when I am talking about traveling waves, but it is not. Uh, there are topics that we can correlate to understand what I would like to express here today to you. And basically, when we analyze the Charles Darwin theory, we see that the evolution happens by natural selection and that a species show variation and physical characteristics due to differences in their genes. We know that also that individuals with characteristics best suited to their environment are more likely to survive. And finally, that individuals that are poorly adapted to their environment are less likely to survive and reproduce. And I, it is worth it to emphasize some parts of these statements that I mean the characteristics best suited to their environment and the word adapted. It is very clear for me that when we talk about evolution, we are talking about characteristics that lead us to be adaptive. Okay, but what being adaptive has to do with being smart? So I took some papers and books in the smart grid context just to analyze if they are correlating the fact of being adaptive with the fact of being smart. And the first one I found that the smart grid supports an adaptive, reliable, and stable power grid, and also that the smart grid consists in a power system capable of self-healing, being adaptive with foresight for event prediction under different uncertainties. I have also found that once we are adaptive, it means that the smart grid has less reliance on operators, particularly in responding rapidly to changing conditions, and also that new algorithms will help smart grids to become adaptive. As you can see here, in the context of smart grid, the word adaptive, 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 we are always talking about being adaptive. Based on that, we can now play together the puzzle game. We started talking about evolution, so we can take this piece and put in the first place, and the evolution leads us to be what? Adaptive. So we can put this piece here. And finally, since we can be adaptive to our environment, it leads us to be smart from the perspective of power systems. That's why this presentation was entitled as being adaptive to be smarter, because I do believe that when we can be adaptive to our environment, we are being smarter. Okay, so keep in your mind this idea, but what probably you are thinking now is, okay, I agree, but what are we being adaptive to? It is necessary to understand the problem that we are facing and why we have to deal with this problem. And in my opinion, the main problem today in travel wave based applications, we can summarize in a term that is uncertainty. So we have a lot of uncertainties in travel waves arrival times because we need to apply travel wave filtering techniques, and it will always exist some level of uncertainty regarding that arrival time. I can highlight here system parameters because based on system parameters, we can calculate propagation velocities, line travel times, and also the line length is also very commonly used in travel wave based applications. And we can state also time references because, okay, when we use single-ended methods, there is no need for data synchronization, but there are two-terminal or even multi-terminal methods that are very popular in this area. and they usually need the two terminal data to be synchronized. And from a practical perspective, sometimes we don't have sure about such an alignment between the time references. So at this moment, we know what is the problem, and we know that we have to solve this problem being adaptive and thereby smart. But I think that some of you in our room may be thinking now that I need further clarification. So I will provide you some clarification on this problem before we talk about the solutions. Um, and today I don't want to present here a class on transmission lines, but I think that basic concepts are very important in order to clarify why we are concerned about these uncertainties. And if we consider a typical line model, this figure here depicts an overhead line, but the same theory can be applied for cable lines, for instance. And in a given transmission line, we will have voltage between conductors and between conductors and the ground. And we have currents flowing through the conductors. So we have magnetic field, we have electric field, and such a way that we can represent this line such as this pi circuit, which is a well-known representation. And what we have to know about this pi circuit is that these parameters here, R, L, G, and C, they are frequency dependent, and on transmission lines, they are distributed over the space. But let's simplify the problem, because we are talking about traveling waves, and when we are talking about traveling waves, we are concerned mainly with high frequency transients. And when we consider these high frequencies, it is possible to notice that the losses, the effect of losses are negligible in comparison to the effect caused by inductances and capacitance. I mean, inductive effect and capacitive effect. In such a way that we can disregard at this moment, just to simplify the problem, we can disregard losses, and we will have here basically an inductor and a capacitor representing the transmission line. So let's consider now that we will take into consideration a lot of incremental parts of this line in order to simulate the distributed parameter of such a line, and that a surge will take place on this left side here in such a way that we will have a step in voltage or current. I mean, it may be caused by a lightning discharge, a fault, a switching maneuver, and so on. But let's consider that the energy at that point will vary, leading the inductor to be charged in magnetic field in such a way that this energy, which will fill this inductor, we can say like that, it will be pushed forward to the capacitor, okay? And this capacitor will be filled, and then the energy will be pushed again forward to the next inductor, and so on, and so on, and so on. So we have the surge propagating over the line, filling these energy gaps just by the interaction between the electric and magnetic fields in such a way that this energy is moving over the space, but the transmission line is static. The transmission line is not moving. So we are talking about an electromagnetic event, okay? And if we consider this line as a homogeneous line, we have a balance between these energies stored in magnetic and electric fields in such a way that if we consider that these energies are equal between each other, so we can obtain a relation between the voltage surge and the current surge, which are called here zeta S, which represents the surge impedance. And basically the surge impedance is what? This is the characteristic impedance when we disregard losses. So just to simplify, let's work with the surge impedance, okay? And okay, we now already know that there is an energy propagating over the line, and we know that this energy requires a time to move from one element to another in such a way that there is a time required to the surge to propagate from one side to the other. And if we have a time of propagation in a well-defined length here of this line, we are talking about a line travel time. And since we are considering that this line is homogeneous, and we have a time and we have a length, so we can talk about propagation velocity. Okay, I know when we are interested on hybrid lines, for instance, the problem is much more complex. But today I will focus on homogeneous lines only, okay? Just to tell you what I came here to explain. So where are the uncertainties? If you take into consideration all these relations, you can conclude that there are uncertainties in all parameters related to traveling wave propagation, because all these parameters depend on line parameters, and these line parameters may vary due to weather conditions, loading conditions, and so on. So, okay, we know that some measures can be taken into account in order to reduce this these uncertainties, but they will always exist. They can be critical, they can be negligible, but these uncertainties will always exist. And the problem is that when we consider uncertainties in surge impedance, propagation velocities, line length, line travel time, these parameters are those that are often used as settings of traveling wave-based applications. Just to show you this problem using some results, we have published a paper in 2020. If you want to take some details on this paper, you can scan this QR code here. But basically there, we are analyzing the differences between EMTP program line models, namely the Bergeron and Jose Marti model. The Bergeron model calculates the line transients considering a given frequency, and Jose Marti model takes into account the parameters frequency dependence. And through this study, we could see that both models are quite different in relation to the traveling wave response. And these figures here show you that these figures were obtained using a well-known traveling wave filtering technique, which has been used in actual traveling wave-based devices. And basically, we took the simulated signals and applied the filter, and here we could see the differences. And then we had the chance to compare this case with the real record in such a way that we could see that the Jose Marti model is much more representative than the Bergeron one when it is calculated at the fundamental frequency, for instance, here in Brazil is 60 Hertz. But what we could see here was that the aerial mode, which is in blue, has a little difference, but there is a difference. And the ground mode is very different. And when we consider that these quantities are decoupled in model quantities, we can analyze model velocities, and propagation velocities of aerial modes are very high here, almost constant, but the ground mode velocities, they vary a lot over the spectrum, okay? They vary a lot over the spectrum. And so we have some differences here, but the question is, when we are in a practical case, what is the frequency of my transients? At what frequency those transients are over the spectrum? We don't know. We don't know. So there is an uncertainty, even for aerial mode components. So we have a problem, okay? And in this case, it is interesting to analyze the literature in order to understand what has been done to overcome these problems. And the first works were published since 1940s or even 1930s. But there are two papers that I really enjoyed to read, which were published in 1956 and 1957. And in these works, they present a bibliography and summary of fault location methods. In the second one, they classify fault location methods for overhead lines, mainly the travel wave-based ones, as types A, B, C, and D. And I would like to highlight types A and D because they are today known as the classical 1 and 2 terminal methods, respectively. And so let's start analyzing the single-ended fault location method, type A. To do so, we will consider the Bewley diagram, in which the horizontal axis here represent the space, distance, and the vertical axis here represent the time. And as soon as the fault takes place here, travel waves will be launched from the fault toward the system. It will propagate until the line terminals, which are which usually consists in a discontinuity. And these waves will reflect back to the fault point and then reflected back to the measurement terminal. And basically, we have here to detect the arrival times of this reflected wave and this first instant wave in order to calculate the time difference between these two arrival times in such a way that if we consider a constant propagation velocity, mainly using aerial mode traveling waves because the velocities are almost constant over the spectrum, we can obtain this formula, which is a well-known formula for a single-ended fault location procedure. But what are the problems in this formula? I can tell you that, in my opinion, and I would like to point out that this presentation is based on a very personal opinion. In my opinion, the practical difficulties here is to detect the reflection and also to estimate the propagation velocity. Many people will say that there is no problem on using propagation velocity, but I have heard from colleagues from utilities in Brazil a lot of times that people have to recalculate this propagation velocity and they wait the next fault in order to refine the values that they are using as settings. And okay, I understand that these values do not vary so much for overhead lines, for instance, but when we are talking about cables, the problem is much aggravated. So in my opinion, this is a problem because we will have uncertainties. But the question is, why detecting the reflection is a problem? Detecting the reflection is a problem because we have to be in mind that the power system has adjacent buses. We have to be in mind that these traveling waves propagate to the opposite side and they are reflected back, passing through the fault and being transmitted towards the monitor terminal in such a way that if you want to detect the reflection that comes back from the fault point, we need to distinguish it from the reflections that come from adjacent buses and from the waves that are transmitted through the fault point. In hybrid lines, this problem is even more critical because we have discontinuities over the line. The line is non-homogeneous, but as I mentioned it earlier, I will not focus on that in this presentation today. So due to these issues, the double-ended fault location method type D gained a lot of popularity. And basically, this method considers that local and remote terminal data are synchronized. And basically, it detects the first wavefronts in such a way that there is no problem on detecting these wavefronts because they consist in the first transients that show up in the analyzed record. And based on that, and considering that we have the same velocity for both of waves propagating towards both line terminals, we can consider that these velocities are almost the same. Okay, we know that they are not exactly the same, but they are almost the same. So we can calculate the inception time of this fault using data from the local terminal and from the remote terminal in such a way that we can derive this formula, which is a well-known formula and that has been successfully applied for years in double-ended fault location procedures. But in my opinion, we have also problems here, also practical difficulties, which consists in the need for knowing the line length and the need for having synchronized data, because we can lose the communication channel, for instance, and lose the GPS signal, so we will not have sure about the data synchronization. The propagation velocity problem has been already explained, and the line length information, we know that it may have also uncertainties. Even though, despite these practical difficulties, this method is the simplest one to be applied in the field because it requires the detection only of the first incident waves. And due to that, in 1972, the Bonneville-Pod administration published a paper reporting one of the pioneer field applications using the Type D method, but they report also that some initiatives or practical applications have been used since 1955. Okay, but after that, considering that such a promising technique, Type D, we could see in the literature, this is my opinion, I have noticed that there is a gap in relation to the proposal of new concepts, new algorithms. And there is a paper that was published in 1993, presented by Philip Gale, Peter Crossley, and other colleagues, which I consider that was the resumption of studies on travel and wave-based applications, mainly focused on fault location. In this paper, they present types A, types B, type C, and type D, but they start to point out some concerns about having to set the propagation velocity in such a way that they present some solutions in order to overcome the need for propagation velocity. And then commercially available devices have been released in the market, mainly from 2008 onwards. And this device presented a very important characteristic that was not possible in the past, that is related with the sampling rate. So in the first device, sampling rates were very low, and the result is that we had some difficulties to apply travel wave-based technologies, but using sampling rates in the order of megahertz, the analysis of travel waves became possible. And in today's technology, we have devices operating with sampling rates equal to 1 megahertz, 1.5 megahertz, 5 megahertz, and there are some manufacturers reporting that in the next coming years, we will have some device operating with 10 megahertz. It is amazing because we can see the event in a perspective that have never been observed. And another important point is that travel wave detection approach have also evolved, either using analog or using digital filtering methodology, but they are evolving still now. And as we can see in the literature now, there are a lot of new developments that we can't be blind to these new technologies because they are very promising in my opinion. Okay, and the question now is, what are these developments taking us in the technological context? And my answer is that the travel wave-based applications are expanding. They are not limited. They are no longer limited to fault location applications. We have high-speed line protection. The protection schemes based on travel waves are not limited to transmission lines. We have already seen some protection schemes focused on bus bars and shunt capacitors and so on. We have seen some travel wave-based algorithms being used to calculate line length, which is information very useful for a lot of applications and power systems. We have seen travel waves being used for predictive fault detection, which is a quite interesting application because they detect weak points on the system that can be inspected before the fault takes place. We have also seen travel noise being used to align two terminal fault records, which is very important from the perspective of post-fault analysis. And these applications are expanding. These applications are expanding. But I have a limited time today in such a way that I will focus on fault location only. So also we have defined now that we will talk about fault location. I would like to invite you to translate all the ideas that we have presented before regarding human evolution and smart grids to the context of fault location on transmission lines. And when I say that, I know, I am not saying Charles Darwin said this. So when they say that species show variation and physical characteristics, we are understanding that algorithms may show variation in their methodologies. There is no problem in that. When they say that characteristics best suited to their environment are more likely to survive, we understand that adaptive solutions are more likely to be robust to system uncertainties. And when they say that being adaptive means that smart grids have less reliance on operators, particularly in responding rapidly to changing conditions, we can understand that adaptive smart methods have less reliance on human intervention, which is one of the most important source of errors to fault location and protection schemes, and responding naturally to changing system parameters. And based on this way to think, I do believe, Professor Felipe Lopes believes that this is a very strong trend for the next coming years. Okay? There will maybe some people that will disregard with my position, but this is my position based on what I have read in the literature over the last 10, 11, 12 years, and based on what I have heard from colleagues from utilities and from my experiences analyzing simulated and mainly real case. Okay. So at this moment, we have to know if the literature is telling the same thing to us. And when we analyze the literature, we can see that we can find some setting street travel wave-based fault location methods, which are independent of propagation velocity, line travel time, some methods that eliminate line length when per unit distances are estimated in fault location applications. We can find also some travel wave-based fault location methods that can operate using unsynchronized data. As a result, they are independent of a common time reference. And mainly, we can find algorithms that combine both. I mean, we can find algorithms that are settings free, and at the same time, they can operate using unsynchronized data. It means that they can accommodate uncertainties in both system parameters and in data synchronization. This is, in my opinion, this is undoubtedly an evolution, and they are being adaptive to their environment because they do not require to set a given value to the propagation velocity, and they do not require to have sure about the time synchronization. In my opinion, this is the way. And however, as you may know, there is no free lunch. And these methods require a counterpart. And my conclusion in this context is that for each variable eliminated from fault location formulas, an additional information from measurement is required. What I mean is, what are the variables to be eliminated? Propagation velocity, line length, line travel time, time synchronization error. And from measurements, what we can include in these formulas, we can include arrival times, of traveling waves reflected from the fault point, arrival times of traveling waves transmitted through the fault point. We can analyze amplitudes or other features perhaps, but in today's technology, using the arrival times of traveling waves reflected and transmitted from and through the fault respectively are the most used solution in order to be adaptive. So we are talking about an additional complexity to be adaptive. And being adaptive, we will be smarter. At this point, I will invite you to play this game. I had a lot of good times with my family, especially with my sisters. And we use it to look at these pictures. In Brazil, we know as Where's Wally, but I know that in other countries, it is called Where's Valdo. And basically, the game consists in finding this guy here in the picture. Okay, I don't have much more time, about 6 minutes to finish my presentation. But if I wait to find Valdo here, probably I will have problems with my time. Because to find Valdo, you need to look at this picture very carefully, paying attention to all the details in order to distinguish Valdo from all of these people in the picture. I have no time, but you need to have attention, and mainly you will need time. And when we are talking about fault location, we don't have time. The goal is to be quick. The goal is to pinpoint the fault point as quick as possible. Okay? So I will provide you the answer. Valdo is here. I don't know if you have already seen find Valdo, but he is here. And what is the relation between Valdo and traveling waves? I would like you to understand Valdo as the reflections, as the traveling waves reflected from the fault point, and as the traveling waves transmitted through the fault point. And these figures here depict some of the most common filtered signals that have been used in real device to analyze traveling waves. The question is, okay, it's very clear that these first transients here are the first incident traveling waves. But where are the reflections? Where are the transmitted waves? Where's Valdo? This is the question. And this is the main challenge here today. Because to be adaptive, we need to give a counterpart to these methods. And we will need to detect reflections and transmitted waves, but this is not trivial. We have to look at these figures, and we have to find these waves, we have to find Valdo. So just you to see that that the literature is not going away from this idea. I would like to present my final slides, reporting some classical papers and also some of my own papers that we have published on this topic. This first one here is a paper published by Mahmoud Jilani and colleagues, and basically they eliminate settings because they consider the first detection of the first incident wavefronts here, but they include the detection of the reflection from the fault point in such a way that there is a formula which is independent of propagation velocity, but this method is still dependent on the data synchronization. What are the practical difficulties here? The detection of traveling waves reflected from the fault point and also the data synchronization. Here there is another paper, very interesting paper, written by O.D. Naidu and colleagues, where they eliminate data synchronization. So to do so, they basically detect the first incident traveling waves, but they include the detection of the first reflection at one side and the transmitted wave at the opposite side, and they derive this formula here. As you can see, they do not correlate here remote and local data in such a way that this method is independent of time synchronization, but it requires the detection of reflections and transmitted waves and also the propagation velocity. Here we have another very interesting paper where Edschweiter and colleagues proposed a very promising method in which they consider the first incident wavefront, but they detect at only one terminal reflections and transmissions. And they obtain a per unit fault distance here to locate the fault using only one terminal. It's a very interesting method, but the practical difficulties are the same. They need to detect the reflection from the fault and transmitted waves. Here is a method that I have proposed in 2016, in which we eliminate the need for the detection of reflections, but we require the detection of ground mode waves. And based on that, we also developed a fault location formula here in order to locate the fault properly, irrespective of the line parameters and data synchronization. I have to recognize that when we are using ground mode waves, we have a challenging task, because these ground mode waves attenuate more than aerial mode ones. And as a result, the detection is challenging. And as I mentioned it earlier, the velocity, the propagation velocity varies over the spectrum in such a way that depending on the transient content that propagate toward the local terminal and the transient content that propagate towards the remote terminal, we may have different velocities, and this is a source of error for this method. But this was my first insight on how we could eliminate settings and data synchronization. And this method evolved then in 2018 to another method that we proposed, in which we eliminate the use of ground modes, replacing these ground mode waves by the reflections from the fault point at both line sides. And by doing so, we could eliminate data synchronization and settings from the fault location formula in such a way that the practical difficulty here is basically the detection of the reflections from the fault. If you think that these methods are only in a scientific world, and this is not true, these methods, both that one that use ground mode waves and this one that use reflections from the fault, they were validated using real data. And what I want to highlight now is, if you want to read this paper, we show a practical approach to apply these methods. And the message is that in today's technology, it is already possible to apply adaptive methods, because we could find that the errors obtained from these methods were smaller than 2 typical tau spans, which is comparable to those errors obtained from classical methodologies, but without needing settings nor data synchronization. We are being adaptive, and as a consequence, smaller. So to finish my presentation, what are the next steps, in my opinion? I really expect that in the coming years, we will see adaptive travel wave-based applications gaining popularity, because they are indeed promising and robust to uncertainties. And when we can detect reflections and transmitted waves, they are much easier to apply in the field, but there is no free lunch. As I mentioned it, we will need improvements in travel wave filtering and detection approach, because detecting reflections and transmitted travel waves is inevitable to be adaptive, in my opinion. And I do believe that we have to expect to increase the experience with real data, because today there is no open fault record library available for researchers, and these advances are very concentrated in the research centers which have some partnership with manufacturers. But we are working in a secret group to build an open library to support research on that. So we do believe that practical experience depends on the analysis of real measurements, and by doing so, we expect to see the development of new adaptive solutions. So my conclusions, uh, we said today that being adaptive can lead us to be smarter, and this is already a reality. Okay, the evolution of algorithms had led them to be adaptive and thereby smarter, as you could see in these papers that I mentioned before. But there is no free lunch. We have to bear this in mind, and a counterpart is necessary, and it will probably motivate the development of improved, enhanced detection of travel waves, other travel waves than the first incident ones, which are those that have been used in the classical two-terminal technique. From the literature review, these solutions have shown to be adaptive to uncertainties in line parameters and time synchronization. So these solutions stand out in this context, and in the next years, we hope to see more real data available to boost research on this topic. And basically, we have to remind that travel wave-based applications are not limited to fault location. They are expanding, and the interest from the utilities is increasing. That's my message to you today. So let's be adaptive to be smarter. That's it. Thank you very much for your attention, and I thank again for the attention of all the audience and for the invitation for being part of so nice of this such a so nice event from IEEE. Thank you very much.
Thank you, Professor Philip. It was really a very nice session, very fruitful, and we learned a lot of things from you. Now, waiting for the audience. If there's a question, we can ask. So, anyone have a question, they can type it. I will ask my question about which variables we can eliminate in the fault location. Like,
Which what, Cha? I'm sorry.
which variables we can eliminate in the.
Okay.
Yeah.
In my opinion, the most critical variables that we can eliminate are propagation velocity and line travel time. There are some manufacturers that have already proposed measures to overcome uncertainties in these variables, like modifying formulas that use it to be function of propagation velocity, and now they are using these formulas as function of line travel times. And these line travel times can be measured during like switching maneuvers of transmission lines. And okay, I appreciate these solutions because they indeed reduce uncertainties in this parameter, but it may occur like you make today a switching maneuver, and the system can change in relation in the period from the commissioning and the fault, the day when the fault took place, and so an uncertainty will exist. As I mentioned it earlier, it can be negligible, okay, but it will exist, and it can be critical. And the main information that I want to emphasize again is that when we see these solutions being applied, they seem to be very simple. But when we talk with people from utilities, they state a lot of difficulties to set these parameters. That's why I am asking all of you to try to be adaptive and to eliminate these variables.
Thank you very much. If anyone have questions, they can type it and Professor can reply to you. I guess there are no more questions here. But we are waiting if someone have
Maybe
question.
the slides were very clear.
Actually, the topic was interesting.
But no problem. If any of if you want to see further information, I am publishing always this information in my social networks, so you can follow us there.
Thank you. Thank you. Anyone have question? They can type it. Oh, okay, there's a question, Professor. Can you explain why transmission line length is in uncertainty?
Yeah, sure. Thanks for the question. Uh, we know that transmission line length is used in most fault location methods and also in some protection methodologies, for instance, it is also required. But we know that the estimation of this length is not so accurate because we have the cable length, and the cable length will depend on those arrows between two sequential towers. But there are some people that estimate the line length as the distance between the towers, okay, in such a way that there is an uncertainty on that. And depending on the weather conditions and loading conditions, these cables can vary their length. So this is a very interesting problem that is scarcely mentioned in the literature, but I have seen some manufacturers concerned about that. And today, we can see also already some proposals to analyze the position of the towers rather than the length in order to dispatch the line crews because they are recognizing that there is an uncertainty. So these cables can vary the length and then we will have some problems in fault location.
Okay, thank you. There's one questions. Can you highlight some challenges that such a technology impose to the protective relays with high penetration of GDs?
High penetration of GGs. Okay, it's a question from Roberto. Thanks, Roberto, for the question. Uh, I have some concerns about that because when we are connecting like wind power generators or photovoltaic power plants, the connection is usually placed on a bus bar, and at that bus bar, the transmission line is terminated by a transformer, which in high frequency is seen as open circuit. And I have read a paper yesterday on that, and we have published a paper some days ago talking about that. We'll need to look at the busbar capacitance and the transformer capacitance, spurious capacitance, I mean. And this spurious capacitance will exist in high frequency, but I do believe that we need to provide further investigation on that in order to make sure that these functions will be reliable. In my opinion, they can, if these capacitance are high enough to make current transients to take place in the records, leading the device to detect that those wavefronts, I believe that these functions can be promising. But for smaller capacitances, we may have a lot of attenuation of these current waves, which are those that have been mostly used in travel wave-based applications. And if these capacitances are very small, we can desensitize the detectors, and so we can have problems.
Thank you. One more questions. Do you believe in future TW-based protection schemes might substitute phaser-based ones?
Okay, this is a question from Professor Kleber, right?
Yeah. Clear.
Good, good. Thank you, Kleber, my colleague, great expert in protection systems. I appreciate your question. Kleber, I don't think so. I don't think so because travel wave based protection requires the travel waves to exist. And as we know, these travel waves may not exist depending on the fault inception instant and fault resistance in such a way that I believe that they can be like some complement. They can be combined with phaser applications to accelerate the protection and to provide for a sensitivity in case in which phaser-based protection doesn't work as expected. But I don't think so. I think they will walk together. Okay.
Okay. Thank you. There's one more question. The discussion is in this presentation is focused on the TW arrival time. What are your comments on the TW magnitudes? Are they reliable for fault location purpose?
Okay. Thank you very much for this interesting question. This is indeed a very good question. But my opinion is we can use. I have also seen some approach based on the amplitudes of these waves. Depending on the filtering technique that is being used, you can have very confident information on these amplitudes. But if you depend on amplitudes, if we are talking about relative amplitudes, my opinion is that can be promising. But if you need a very accurate amplitude measurement, I have some concerns because this amplitude will depend on the characteristic impedance of the monitored line, for instance. And this characteristic impedance, as we mentioned during the presentation, will have a lot of uncertainties, mainly in ground mode. So if you depend on that, you will have to deal with the problem of uncertainties. Okay, but this is possible, and there are some solutions that are working like that.
Thank you very much. Yeah, I guess there are no more questions, but waiting if there is question, so I can tell you.
Okay, Shah, can
Yeah,
I say some final words here? I I would like to thank again for Luis,
yeah,
who have invited me together with Study and
yes.
all the support. This is an amazing event, and this is a great pleasure for being here today. Okay,
And
so I really appreciate the invitation and count on me whenever you need. Okay, thank you very much.
it's an honor for us that we are delighted and from whole team. I'm very thankful to you for giving us the time. We are really happy. We appreciate your work, your knowledge, and it's an amazing event. And we learn a lot from you. And hope in the future we will also invite you again for further topics. This is
Okay.
really very happy. Yeah. Thank you very much for your time, Professor. And thank you, everyone, for joining us and for asking such amazing questions. Thank you,
Thank you very
Professor.
much.
Thank you, Professor.